How's everyone doing? Can you hear me? Awesome. I'm hanging in there. I have not slept that well the past few nights, as I expect many of you have not. If you're paying attention to the news, but it's a nail biter. But it is what it is. Other than that, I'm fine. Getting a lot of work done. How are all of you? Once again, the kitten is awake and just off screen, so apologies if she interrupts today. I'm all right. I'm tired. Definitely tired. But I think this is a pretty cool lecture, and that was not just an ice joke. So hopefully that will be, hopefully that'll keep everyone sort of invigorated with interesting things that aren't politics. Wait until it's exactly 2 again. It feels like weirdly quiet right now, but I will wait. All right, so it is 2 now, so let's get started for real. So today's topic is going to be glaciers, and so this is going to be another one that's just a one lecture topic, and these slides will go online immediately after class, and the video will go up on YouTube as soon as my internet connection allows that to happen, sometime later today. But this is actually our last topic before the third test, so again, time is kind of crazy, and it feels like, I know it just feels like we just had the last one. But our next test is actually coming up on Monday. And it's going to cover all the stuff since the last test. So it's going to be sedimentary rocks. It's going to be mass movements, rivers and floods, and glaciers. So all of the stuff that's on those study guides is the stuff that you're accountable for. And so if you haven't been looking at the study guides, please definitely look at them on Canvas. They're up for every topic. And just sort of quiz yourself by going through each point on them and going, okay, Can I explain that? Do I know this definition? Do I know the difference between these things? Just sort of quiz yourself. And then if you don't know, go look it up in the book or go back to the slides or the videos or send me an email. I'm definitely glad to keep helping with stuff up until right before the test. After today, I will put up another one of those polls for if there's stuff that you want me to go over on Monday before the test, then I can do that. It'll work the same way as last time. So we will meet in here at 2 o'clock on Monday and spend about 25 minutes doing a last second review. And then the test will be available starting right at 2:30 and going until 3:15. It is going to use Lockdown Browser again. So even if it has worked fine for you in the past, please double check that it still works before Monday. I'll email you all about that on Sunday as well, but definitely just make extra sure that you can still open that test and that Lockdown Browser is still working on whatever device you're using. Because I did have a couple of people who had no trouble with it on the first test, have trouble with it on the second test. So just check in advance and save yourself that stress. But yeah, that is going to be Monday. So does anyone have any questions about that? About the test, about logistics or anything? Cool. So I will also get all of those quick quiz grades up to date. So for the ones that were, they're like, you can't get a 0 on a quick quiz unless you don't do it. So I'm going to go through and update those after class today. There will also be one more quick quiz that goes up after class today. And also do not forget to do those practice problems for the river discharge. So as it turns out, I had initially accidentally set that to say that you could only do it once, which is wrong. You can redo that as many times as you need until you get the number of points that you want. And so I've changed it, so now you can do that. So like if you did it and went, man, I got 2 points out of 5, I want another shot, you can absolutely get another shot. So just you can keep redoing that over and over and over until 2 p.m. on Monday. So that's kind of the state of things. And then we don't have class next Wednesday, the 11th, because that's Veterans Day. It's a state holiday or federal holiday. And then our next actual class will be a week from Monday. And that's when we'll start talking about metamorphic rocks. And that's our 4th unit. So that's just kind of the state of things. Any general questions about the test, anything else, the rest of the semester, life, the universe, and everything before we get on to today's actual topic? Cool. Then I'm going to get started. As always, if you think of stuff, just put it in the chat or just ask me. And my guess is that this is going to be a shorter lecture today. We'll see how it goes. I mean, there's plenty of time for questions, but yeah. So yeah, today we're going to talk about glaciers. So if you're still bemoaning the fact that it's 93 degrees in Northridge right now on November 4th, think about ice. It'll hopefully help. But anyway, so I guess this first slide kind of gives some stuff away, but about what a glacier really is. But like when I say glacier, just like you currently chewing ice, nice. When I didn't put ice in my water bottle and should have. But when I say glacier, like what does come to mind for you? Iced coffee. Okay. Yeah, ice. But when you think about glacial ice, like do you think about it as a big chunk of ice? Like is there anything that you think of other than it just being very large? A glacier the size of a large glacier. Yeah, they can be destructive, although most of the time they move slowly enough that they're not. Yeah, they're cold. They are melting. They are very much melting. There are many fewer glaciers now than there were even 50 years ago, let alone 100 years ago. So glaciers very much move in. They have cycles that are driven by not human-related climate things. There have been advances and retreats over geologic time, but since the Industrial Revolution, since the late 1800s, humans have put so much crap into the air that it is very much heating the planet and melting the glaciers. So we're not going to have a lot of time to talk about that in this lecture, just because of the amount of time we have. Although if you have questions about that, there might be some time at the end. But just in terms of, we're focusing more on basic glacial processes in this lecture. Because yeah, you might think of them as being just a big chunk of ice. The fact is that, like so many other things on Earth, that, you know, if you just sit there and stare at it, you're going to be like, this isn't moving. It's pretty, but it's not moving. But glaciers are absolutely a very mobile thing. In fact, by definition, a glacier moves. A glacier is a sheet of ice or a river of ice, and it has to be frozen all year. Like even in the summer, it's still got to be cold enough and enough of it to stay frozen all year. And then it actually moves across the landscape. So like if you just have a big chunk of ice that isn't moving at all, it's not a glacier. Or if you have something that like there isn't ice there in the summer, but there is every winter, even if it's every single winter, even if it moves back and forth during that winter, if it's gone in the summer, it's not a glacier. It has to be year round. And definitely like it's the kind of thing where the internal coldness of a glacier, because there's so much ice in there, is that it can stay frozen even at warm temperatures. So I visited Alaska in 2014, and we went on a field trip that involved going to a glacier, and it was like 65 or 70 degrees outside. I was out there in a t-shirt, and I have this, I should have put it in the lecture, this like glacier selfie where I'm there in a t-shirt with this giant chunk of ice behind me, moving chunk of ice, wasn't visibly moving. And I had a lot of people comment on that going like, weren't you cold? You're from LA, why aren't you cold? And I'm like, it was 70. It was May. But yeah, they stay frozen all year and they move back and forth. And so that perennial frozenness and that motion are what distinguish a glacier from a big chunk of ice. So does that make sense? Cool. So it's a slow movement. It's not something you can necessarily see if you stood there and stared at a glacier. But a time lapse, oh yeah, I forgot to mention, this picture is on the first slide is in the Austrian Alps. So this is in Europe. And these, I believe this one that I'm going to show you is also from the Alps, but I might be remembering wrong. So yeah, you can't, like if you were to sit there and stare at a glacier, you wouldn't necessarily see it moving. You might go, okay, wow, it's at a different distance at the beginning of winter than it is at the end of winter. Like it has to have moved to change places. But it is something that a time lapse can show. And so I'm gonna jump ahead to the time lapse in this, and you're gonna see this glacier move.
There is a way to see it move.
So even though this might look like the avalanche,
camera shows that unexplained surface ice travels at around 275 meters per year, carving away the rock as it goes.
I'll pause that for now. This whole video will be on Canvas. But yeah, Elaine says it looks like an ice river, and that is exactly what it is. It is basically an ice river. It is flowing ice. Even though it's solid, it's flowing. We'll talk more about how in a bit. But yeah, even though that time lapse looked kind of like those avalanche or landslide videos we looked at, like this isn't happening all at once. This is happening like the voiceover said, like 275 meters per year. That's like a quarter of a mile-ish per year. So it's not like a massive, massive distance. Like this is slow, but it is moving. And when you speed it up, it absolutely looks like the river that it really is. And often in places where then in the summer, if the glacier has retreated further back, you actually will get rivers of liquid water flowing out from the base of the glacier. But yeah, this stuff moves. And this whole 4-minute video, it's 4 minutes, will be on Canvas in this slide presentation later. But there's a lot of voiceover in it, so I don't want to play the whole thing and talk over it. But yeah, whoops. So glaciers are, I mean, they're ice rivers. Yeah, and so but they actually share properties with a lot of the stuff that we've already talked about, and some stuff we're going to talk about soon. So glaciers, as we just established with that observation, they're a lot like streams. They're flowing. They flow in a channel. They have a lot to do with mass movements. Like if you remember those videos we watched of landslides and slumps last time, the movement of the ice very much looks like that and actually has some very similar physics to landslides, which we'll talk about in a bit. But aside from those motions, they're also just the way that glaciers form has a lot in common with how clastic sedimentary rocks form. And then actually it also has some things in common with metamorphic rocks. So the reason this is our last lecture before the next test is that it kind of ties together all of the sedimentary stuff we just talked about and introduces some principles that we're going to get into a lot more depth on when we start on metamorphic rocks the week after next. And so what I'm going to do now is just go through how these things are, like why glaciers have things in common with all of this. And so I'll start just with sedimentary rocks. But if you think about it, what has to pile up for a glacier to form?
Water?
So if it's liquid water, is it going to turn into a glacier?
No. Wait.
Yeah, no, it's not if it's liquid. So
Yeah.
in order to pile up frozen stuff, what has to pile up?
Ice in that case?
Yeah, so ice has to accumulate, but where is it coming from? Snow, exactly. Yeah, I was about to say what process that we never have in Los Angeles happens in cold places. Yeah, snow is actually where that ice originally comes from. But think about snow. Think about how snow falls, even if you've never actually seen it fall yourself. Like surely you're already seeing all of the like Christmas ads with snow in them because Halloween happened and now it's Christmas season, I guess. Think about snow. How does it fall? Like does it fall as just like onto the ground? Slowly. Yeah, so well, actually sometimes it can be pretty fast, but it's fluffy. So what is, like, does snow fall as what? Fluffy is a very important point. But like, yeah, snowflakes, exactly. So it's this, snowflakes are individual little mineral crystals, right? Because ice is a mineral. It is naturally occurring, has a crystal habit. It forms in, again, it has a chemical formula that is that. Like ice is a mineral and a snowflake is just an ice crystal. And so if you think about, like when you're building a sedimentary rock, you pile up a whole bunch of grains of either rock particles or minerals, right? And then you crush them together until it turns back into a rock. Well, snowflakes are kind of a lot like that. Basically, snow is clastic. If you think about like every sedimentary rock, each clast is a grain of something. Well, glacial ice, the clasts are snowflakes. You can, like if you plant yourself down in a snowbank and look at it, you can see the individual snowflakes. Just like if you look at a piece of sedimentary rock, you can often see the individual grains. Although if you try to lick this rock, it's just going to melt, but because it's ice. But snow is clastic. And so in a way, the buildup of a glacier is extremely much like the buildup of a clastic sedimentary rock. I mean, instead of weathering, you just have weather. It snows. But in that case, yeah, you have, you could say, yeah, the snow is the erosion. I mean, this is not a word we would use for snow, but like technically, if you have the, erosion is the snowflake leaves the cloud. Transportation, it's falling. Gravity is the transportation mechanism, and sometimes wind. And then deposition is when it hits the ground. It's a lot like a lot of other kinds of windborne sediment. And then just like sediment, if you pile up enough of it, it starts squishing together in a way that all of the air between the grains becomes stuck together. And sometimes a little bit of liquid water then freezes in there and sticks it all together. So the formation of glacier is very much like the formation of a clastic sedimentary rock. Does that make sense? So, clastic sedimentary rocks don't flow, and glaciers do. But, whoops! I guess I spilled water on myself again. But let's keep going then. So, glacial ice, in that way, it forms like a sedimentary rock, but it also has some stuff in common with metamorphic rocks. So if you remember our definition of a metamorphic rock, it's that it's something that starts with a certain mineral structure and starts with certain components, but then due to heat and or pressure, it actually changes its structure and becomes something else. And so it might have the same chemical composition as the sedimentary or igneous rock that it started as, but due to that pressure and or heat, it turns into a different structure. And so glacial ice is a lot like that as well. It starts forming in a sedimentary process, but then basically goes through a metamorphic process to become what it is. And so think about a regular like ice cube, or like think about a snowbank. Like what color is it? Like not a trick question. Like what color is snow or ice?
It's transparent, right?
Yeah, it's transparent or white. Yeah, clear or white. I mean, we're not dreaming of a blue Christmas. I guess that's a different song. But in this case, glacial ice. This is a picture of glacial ice on the left, and it is blue. And that's because the change in the structure of those ice crystals, the change in the structure from a snowflake, which is a very classic ice crystal, into a glacial ice situation, actually changes the density, changes the structure, changes the amount of air, and therefore changes the color. So glacial ice is going to be blue, even if like a snowbank or an ice cube is going to be white or clear. And so what happens to that? Obviously, it's not heat, because if you heated it up, it would melt. In this case, it really has a lot to do with pressure. And it's pressure over time, just pressure from snow building up on snow, building up on snow. And so like when snow falls on the ground, it's very loose. Elaine said fluffy, which is a very good way to describe it. And that's exactly, especially what you want if you're skiing. You want it to be nice and fluffy. And that's because you have these very discrete hexagonal ice crystals that are snowflakes with a lot of air between them. Because the shape of these crystals, all these little sticky out bits, kind of get stuck together and are able to hold a lot of air between them. Kind of like if you think back to our igneous rock stuff, how those big complicated framework silicates like in quartz and in feldspar have bumpy structures that kind of allow them to get stuck on each other and hold a lot of air between the molecules or crystals. And so in that case, your loose snow is kind of going to be a lot like that. But the metamorphic process that turns loose snow into glacial ice just comes from compacting that air and just from squishing things more and more and more. And so at first it just gets compressed a little bit and becomes what we call granular snow, which, loose snow might be up to 90% air. It's going to be more air than water. But as you start squishing it, it becomes less and less air. So granular snow, you might see that the snow crystals, the ice crystals are still hexagonal, but a lot of the really sticky out bits have been worn down. Kind of like if you were taking a very, sharp clasp of something and let it weather down a little, let it round out as it traveled. That's kind of what's going on here. And so with less air, it becomes more dense and more closely packed. And that keeps happening and happening and happening. So when that gets down to only being 25% air, You stop calling it snow and you call it firn, F-I-R-N. And that often takes up to 10,000 years to happen. And so this is still, it's pretty slow. The speed at which glacial ice forms is, there are rocks that form faster than this. So even though we think of ice as something that freezes and melts pretty quickly, this is a process that takes the same amount of time as rock processes can. But yeah, by the time it becomes firn, you can see it doesn't look like snowflakes anymore. It doesn't look like hexagonal crystals at all. It's kind of these little well-rounded tiny clasts, like what happens when you let something transport for a while, that are packed very closely together. And then that compaction just continues and continues and continues. And so you can have glacial ice that is fine-grained, and because these are just continuing to, and so actually, sorry, I missed a step. So firn is still a step where these are weathered down from the snowflakes. But then kind of in between, and so up to here, it's still kind of a sedimentary process. But beyond that is when it really starts to become a metamorphic process. So these firn chunks are just sort of the cores of the snowflakes. But then as the compaction continues, the crystal structure actually begins to change. The pressure actually affects how the molecules stick together. And so it actually, in this case, you start getting small ice crystals first, kind of like, if things are, you're going to build small crystals before you can build big crystals. If you think about our igneous rocks, the ones that cool out in the open air are going to be smaller because they've had less time to form crystals. But the longer and longer that this ice is compacted, the larger and larger the crystals can go. So really old glacial ice, deep down, like 2 kilometers deep. So like that's like 1.5 miles deep into a glacier that's been forming for over 100,000 years. It's going to be less than 20% air, mostly in bubbles, not in the guts of the ice. And it's going to have these very large ice crystals that look nothing like snowflakes because those snowflakes got squished to the point of just turning into something else. So does that make sense? I know I said a whole lot.
I have a question.
Yeah.
So if you were to take that sort of fine grain ice or like the coarse grain ice, would it still have the hexagonal crystal habit?
No, it actually has a pretty different crystal shape. It's more irregular. And so as it turns out, this will make more sense when we talk about metamorphic rocks. And to that point, I'm not going to ask you a lot about the structure. I'm not going to ask you about like the details of the structure of this ice on the test. I'm just going to ask you kind of the process by which this becomes something else. Like, so I'll want you to understand that like, this is kind of a sedimentary process of weathering down, but then it's a metamorphic process of recrystallizing into a different shape. Because as we'll talk about the week after next, metamorphic rocks are, have crystals that have changed shape. And very often there are things, you can have 2 minerals that have the same chemical formula and a different crystal shape. And so that's kind of what's going on here. Does that answer your question?
Yeah, it does. Thank you so much.
But yeah, don't worry about the shape of these crystals so much as knowing whether they're loose or dense, big or small, if there's a lot of air or a little air. Know that it starts as a sedimentary process and kind of becomes a sedimentary accumulation process, and then it becomes a metamorphic crystals changing shape process as more and more air gets squished out. Does that make sense? Are there any questions about any of this? Did it occur to you that you could have a like 1.5 miles thick sheet of ice? Because that is very much a thing. So this figure is in your book, by the way. So if you want to see that again in another place other than Canvas or YouTube, it'll be there. But yeah, if there are no other questions on that, I'll move on. But if you do think of some, just go ahead and ask them. Yeah. All right. So there are 2 major kinds of glaciers. And the difference is not just in where they form, but also kind of in the way that they flow. So like water, ice is going to flow downhill. I mean, it's just frozen water. It is going to flow downhill, but kind of what the downhill is varies depending on the type of glacier. So you can, the first kind on the left here is called a mountain glacier or an alpine glacier. And so those, as you might expect from the name, form at the tops of mountains, because the tops of mountains are, they're higher up, they're in colder air, you're more likely to get a whole lot of snowfall at the top of a mountain, and it's more likely to stay cold enough for that snow to stick around and pile up and become a glacier. And so basically it's too cold for ice to melt, and so you get glaciers. And when these flow, they flow downhill. They flow down the mountain like liquid water would do. So with this example, so this thing here is a glacier. And you can see like it starts pretty much not at the tippy top of the mountain, because that snow is going to still sort of end up in, it's going to go downhill into a place where it piles up. But in this case, this glacier will flow down the mountain. And can you see that even though the glacier itself stops right here, there's kind of this sort of track. Do you all see this area? So that's kind of like a river channel. That's where this river of ice will flow when there's enough ice for it to flow. And you also can see there's actually streams of liquid water flowing down there, because I guess at this point in this picture, it's warm enough that this is as far as ice can stay frozen. And so you get flow as liquid water. But yeah, it starts at the top of the mountain and goes downhill, which again, if you just think about the shape of a mountain, and think about water wanting to flow downhill, you can hopefully remember that a mountain glacier or an alpine glacier will flow downhill as well. I am going to use the word mountain glacier, but I think your book uses both, and you might see both. Meanwhile, the other kind of glacier is called a continental glacier. So and these are enormous sheets of ice that cover even flat ground. And so like if you're hearing about Antarctic ice sheets, Arctic ice sheets, Greenland ice sheets, all of those things where the news is talking about ice sheets melting, this is what they're talking about. And basically these form in places where it's just really cold, and it just is really cold and snows a lot. And it's cold enough that it doesn't have to be at high elevation to snow a lot. So it just does, and it piles up and goes through that same process. And these are generally much larger in every way. They're thicker and they're wider. They cover, again, like the entirety of Antarctica, whereas this glacier is just the top of this mountain. These are gigantic. But even though they're just kind of sitting on flat ground, where there isn't necessarily a downhill on the underlying ground, you still kind of have a downhill within the glacier. So remember when we were talking about mass movements, and we were talking about the angle of repose, and we were talking about how like stuff can pile up, like you can make a pile of sand. And if you make a pile of sand, like if you're just pouring sand on the ground, is it all going to pour in a flat layer? Yeah, no, it's not. You're going to get a pile, and it's going to be the highest at the top, and the highest and narrowest at the top, and then it's going to make a little hill. And so continental glaciers are kind of the same. They're the same idea. It's just a very subtle slope. You might not be able to see it because it's such a gentle curve, but it's still just, you're going to have the thickest amount of ice at the middle of that glacier. And then it's gonna flow outward at the edges, and then also inward at the edges. So like when you see maps of potential ice sheet melting, it's not talking about the whole thing getting thinner. It's talking about the edges pulling in and covering less area, because it's flowing inward and outward at the edges, rather than just because of that sort of slope internally, rather than just flowing downhill. So does that make sense? I think if I remember correctly, this picture is Antarctica on the right. But yeah, and this is still the Alps on the left. But does anyone have any questions about the distinction between mountain glaciers and continental glaciers? then let's keep going. So glaciers move. They move a lot. They're defined by movement. And that movement depends on a balance between two things, accumulation and ablation. So accumulation is exactly what it sounds like. It's stuff accumulating. It's from snow piling up. The glacier will grow if there is more snow. So if rhymes help you learn, remember that. But yeah, just like you talk about snow accumulation in the mountains, that's a weather forecast word. And that exact same process is what contributes to the growth of a glacier. So even if you have a absurdly cold year, if there isn't more snowfall, the glacier isn't going to move. It's not just going to slide down the hill. It's always going to be rooted in the top of the hill. And so in order for it to move forward, you have to add ice. That's why it's, growth, not just movement. So does that idea make sense? Yeah, so again, just think about the word accumulation. What does it mean? The same it means in other contexts. But the other balancing thing is a word that you're probably less familiar with. So has anyone here heard the word ablation before? I already see a quick no. Has anyone ever heard this word? Yeah. So if you haven't, I wouldn't expect that you had. It's not a word that people commonly use. But basically, accumulation and ablation are opposites. Accumulation is you build it up, and ablation is it goes away. It is a fancy word for removal of ice. And there are a few ways that can happen. One of them is just melting. So melting is a kind of ablation. We all know what melting is by this point. But yeah, melting is the most common kind of ablation. It happens seasonally. It happens when it gets warm. It's really, for the most part, when you're talking about a glacier moving, you're talking about more snow falling in the winter and the glacier moving forward. And then some of that ice and snow melting in the spring and the glacier moving back. That is the most common. But there are a couple of other ways that ice can be removed from a glacier. One of them is called sublimation, which is basically direct evaporation from ice. So something goes from frozen, from ice, to gas, water vapor, instantaneously without being liquid water for a while. So that generally requires going from really cold to really warm really quickly. And it'll often happen in spring, where you have the toe of the base of a glacier in direct sunlight, and it's just beaming down on it and evaporating. So less common than melting, but definitely still a thing that happens. Just skipping the liquid water and going straight from solid to gas. And then the last kind of ablation is the kind where someone, who was it that mentioned that glaciers can be, Mariah mentioned that glaciers can be destructive. And the thing that makes them potentially destructive is actually this last process, this thing called calving. And no, I do not know why it's called that. I mean, I guess this is a word for chunks of the glacier breaking off. I mean, I guess it's kind of like, when a mommy cow has a baby cow, it made a smaller cow, which is called a calf. I guess whales and walruses and other things that live near glaciers also have calves. So maybe they were thinking of that. Oh, look, the Arctic whale had a calf. Oh, look, the walrus had a calf. Oh, look, the glacier had a calf. I don't know if that's why they named it that. I really don't. But if that's a way to remember it, that's hopefully that'll help. But yeah, it's just the process of a chunk of the glacier just falls off. Sometimes it's a small chunk and it doesn't really do much. But if it's a really big piece of glacier, first of all, it can crash into things. But also, if it's a really big place, it can actually even cause some localized tsunami-ish behavior, because it's just dropping so much stuff into the water at once. So yeah, it is spelled calf for animal, CALF. But if you were going to use it as a verb, it would be with a V, because English is English. So yeah, calving is if you were to look up, yeah, it's just English. Does this make sense? So does anyone have questions about any of these? Want to see a glacier break? In a video, like not like in the future. Cool. So this video, I think it's about 4 minutes long, and I think we're probably going to watch this whole thing because I think we have time, and it's amazing. So this is from an excerpt from a movie called Chasing Ice. So if you think this stuff is really interesting, both from just the physics of it or the beauty of it or the climate implications of it, it's a really awesome documentary. But apparently this calving event that I'm going to show you here is I think the largest one ever caught on film. I think it's from 2016. Anyway, I think we have time to watch this whole thing. It's mesmerizing.
On the phone with Jim on one of our regular check-ins. Jim, just nothing's happening.
It's going well. We had some serious bouts of wind, but other than that, things are fairly well set up. We've got some time up.
It's starting, Adam. I think Adam is starting.
So like with landslides, these usually give warning. You can usually see cracks and signs that the glacier is going to fail.
Yeah, in that V section right there. Holy shit, look at that big bird rolling. Okay.
Oh yeah, this super 100% can lead to avalanches. Like there's avalanches going on all over this thing. Like all of this stuff. Yeah. That is an avalanche on top of a calving event. Whoops, no, I did not mean to do that. Let's find where we were. Okay. You can see the liquid water beneath there as well. Because a lot of times, even though glaciers are based on land, especially continental glaciers like this, they do sort of end up flowing out over ocean water, which is why often actually contributes to the calving process, because the ocean is moving around under there and is very forceful and can cause cracking and weakening of the glacial ice. Are there big glaciers the size of small glaciers, or does that only work with boulders? It works with whatever you feel in your heart.
The calving face is 300, sometimes 400 feet tall. Pieces of ice were shooting up out of the ocean 600 feet and then fall. The only way that you can really try to put it into scale with human reference is if you imagine Manhattan. All of a sudden, all of those buildings just start to rumble and quake and peel off and just fall over, and roll around. This whole massive city just breaking apart in front of your eyes. We're just observers. It's two little dots on the side of the mountain. We watched and recorded the largest witness calving event ever caught on tape.
So how big was this calving event that we just looked at? We'll resort to some illustrations again to give you a sense of scale. It's as if the entire lower tip of Manhattan broke off, except that the thickness, the height of it, is equivalent to buildings that are 2.5 or 3 times higher than they are. That's a magical, miraculous, horrible, scary thing. I don't know that anybody's really seen the miracle and horror of that. It took 100 years for it to retreat 8 miles from 1900 to 2000. From 2000 to 2010, it retreated 9 miles. So in 10 years, it retreated more than it had in the previous 100.
Yeah. So isn't that insane? So most calving events are not that large. As they were saying, that's the largest one that's ever been caught on camera and is very much influenced by human-related climate change. But this same kind of process happens on smaller scales in a lot of glaciers. And there's even things like one of the big things that you can do at like Kenai Fjords National Park in Alaska is actually get on a boat and watch some smaller calving events. I found a lot of videos of things like that when I was trying to find this specific video again. So that I haven't seen that. I would super like to, but yeah, this is a thing that happens on glaciers. It's just this particular one is just, I mean, it's the size of Lower Manhattan. So any questions about that? And this will also be in this slideshow on Canvas after class if you want to watch it again. Yeah, pretty crazy. But honestly, most glacier movement is just related to freezing and melting. This is a pretty exceptional event. So yeah, as we said on the other slide, glaciers advance when accumulation exceeds ablation and retreat when ablation exceeds accumulation. So if more snow is falling than there is melting, okay, I see a question. I'll get your question in a second. If most snow is falling than there is melting, the glacier is going to move forward. And if more melting is happening than snowfall is happening, the glacier is going to pull back. So the question is, why is it called Greenland if it's full of ice, but Iceland if it's full of green areas? I don't know. I think a lot of it, I'd have to look that one up because a lot of people make that observation. Iceland also does have actually incredibly gigantic glaciers. So my background image today is Vatnajökull in Iceland. They're huge glaciers in Iceland. And there would be more of them in Iceland if it weren't for the extreme volcanic heat under most of it. But yeah, I've never seen a good answer for that. My guess is that it has to do with, I also don't know which one was named first. I believe Iceland might have been first because a lot of the sort of initial settlement in Greenland were people coming from Iceland or even from Denmark. They kind of started, or at least a European settlement. And they're honestly, the native settlements had totally different names for it because Europeans like to ignore existing names and change them. But for the European names of Iceland and Greenland, I think Iceland had people on it first and was named first. But I can try to look up that history and maybe put it on the forum on our on our Canvas. I'm guessing that it is Vikings related. This is probably something that Vikings named. There was also actually Vinland, which was an original name for a part of Canada. But no one knows exactly where the Vinland settlement was because it never really succeeded. But it's thought that, the people went from Denmark to Iceland to Greenland to Vinland/Canada in terms of Vikings arriving in places and trying to give them new names. But yeah, I can look that up. But yeah, getting back to glaciers moving. Actually, there was an NPR story about Iceland and Greenland and Vinland very recently, but I digress. Glacier movement. Glaciers are not going to move that far from Iceland to Greenland. Even the biggest ones, probably not going that far. But maybe I guess in the Ice Age it might have. But modern glaciers, let's talk about the example of a modern alpine or mountain glacier moving. And again, it's that idea, if there's a lot of snowfall, you're gonna add more snow to the glacier, and it's gonna be able to develop more ice and grow. And it's also just gonna be heavier and have an easier time flowing down the hill. So if you think about all that stuff we talked about with mass movements last week, how if you add weight, gravity is gonna have more to work with and pull it down further, that's kind of at play with glaciers as well. So these three pictures, these are in your book, but they're kind of illustrating the movement of glaciers with different things. And so it has this equilibrium line that basically says this is kind of the center of balance. So like if you think about the center of gravity, like let's say you're trying to balance something on your finger, something like a pencil that's about the same weight on either side is going to balance pretty close to the middle. But like let's say you were trying to balance a hammer on your hand, the head of the hammer, like the balance point would be much closer to the head of the hammer because it's a lot heavier. And so in this case, the equilibrium line is like, where is there, where is it that you have more going on versus less going on? Is there more mass at the top or the bottom? So in this case, like, this is just a glacier in equilibrium. It's in balance. You might even say it's at its angle of repose. So in this case, there's exactly the same amount of accumulation as there is ablation. And so the line of equilibrium is pretty much in the middle. Also worth noting, we talk about glaciers as having a head and a toe as well, just like we talk about with slumps. And so if you look at the shape of this, doesn't it look like a slump? You've got your head scarp, your curved line between the glacier and the mountain, and then the sort of bulging toe. So if you don't remember that about slumps, definitely go back and look at it. But a lot of the shape and movement style of glaciers is very similar to the shape and movement style of slumps. It's just glaciers are ice and slumps are dirt or rock. But yeah, here things are nicely balanced. But now let's say this example on the bottom, if you have a whole lot of snowfall and not very much ablation, not very much melting, then the line of equilibrium where there's the same amount of stuff above and below is going to move down. And so if you have more snow and not much melting, that's just going to push the sheet further. It's going to keep going. It's going to pile up and push things down. And the toe of the glacier will advance. So the head is still going to stay where it is. It might get thicker, but it's going to stay where it is. But the toe is really what pushes forward onto the land further out from the mountain. So does that make sense? I don't see anyone saying it doesn't, so I'm going to keep going. So this one over here is kind of the opposite scenario. It's where a situation where there isn't a lot of accumulation and there is a lot of ablation. And so the volume of material down here is reducing very quickly. And so in this case, like accumulation will happen more towards the head, higher up where it's cold. Ablation will happen more towards the toe. Whoops, come back. No, more towards the toe, where it's further down the mountain and warmer. And so in this case, if you're reducing the volume of material here very quickly, the equilibrium point is going to move back up because there's more stuff up here and less stuff up here. So even though this is longer than up here, it's going to be thinner and have less ice. This is kind of the equilibrium. And so the more and more ablation there is, the more and more melting or calving or sublimation you have down here, this is going to start retreating. Both just because this is where the material is coming off of, but also because of that point of equilibrium, because it's going to pull back to try to keep this thing balanced on the side of the mountain. So does that make sense? So if I were to ask you something about like what is going to make a glacier advance versus what is going to make a glacier retreat, or like where is most of the movement happening, just sort of think about that in terms of looking at that study guide and preparing for that test. So are we good to go here? So we talked about what makes glaciers move. We talked about accumulation and ablation, but like, think about what we talked about, think about what we watched, just like, how do they move? What allows this ice to move? What do you think?
Maybe gravity in its own weight.
Yeah, so gravity and its own weight are definitely part of it. But is it like, what is it actually going to do relative to the ground? Like, is it moving with the ground or over the ground?
Over?
Yeah, so it's moving over the ground. I mean, it's definitely dragging some stuff with it, but for the most part, it's moving over the ground. And so when you have something solid and rough moving across something else solid and rough, do you remember what force might be involved there?
I want to say stress.
So stress is involved, but what is keeping it from just sliding all the way all at once?
Friction.
Friction, yes.
There
Yes, I
you
see.
go.
So you said friction, Diana said friction, lots of people said friction. Yes. It's the same thing, like if you're thinking about mass movements, about landslides, about rock sliding over rock. It's actually going to be important for earthquakes too. But if you remember, I said this is a lot like a slump. It's a whole lot like a slump. And in this case, you have friction between the mass of ice and the rock that it lies on top of. And so that friction is actually part of what can hold this up here on such a steep slope, but what still allows this to slide forward. So it's kind of a balance of friction holds this in place, but then as this moves, it still generates a lot of friction. And it is also what friction that sometimes allows it to stop where it is, in addition to the temperature situation. It slides around the ground. It's like a mass movement. It's very much like a slump. And actually that frictional sliding of ice against ground sometimes produces seismic signals. So we're going to talk about earthquakes a lot more in like a month from now. But earthquakes release seismic waves. The shaking you feel from earthquakes is caused by the friction of rock moving past rock. And so you can actually get, what's called ice quakes or glacial quakes that are from the movement of ice against the ground, from that frictional sliding. But yeah, in this way, so yeah, a glacier does some stuff like earthquakes, but it's very much like a mass movement. Like if I were to take the word snow out of this chart and just color it gray versus gray, like you would have a hard time telling. Like if I were to take all of the words off this and just show you the picture, you would probably have a hard time telling if it was a slump or a glacier because the mechanism and the shape is so similar. So does that make sense? I promise I'm not going to do that on the test, by the way. That would be mean. I'm not going to take all the labels off this and be like, what is it? But I might ask some questions about how those two things are similar. Am I good to go on with this? So frictional sliding is part of it, but it's actually not the only thing. So another thing that really is important for how glaciers move is actually another kind of metamorphic process. So don't worry about this too much right now. We'll talk a lot more about this process when we talk about metamorphic rocks. But this is still a concept when we went back at the very beginning of the class, when we were talking about how you can have convection in the Earth's mantle, how things like the asthenosphere and mesosphere, despite being totally solid rock, still flow. And that's due to something called plastic or ductile deformation. Plastic because it is able to flow and deform. It's not literally plastic like my water bottle is plastic, but it moves like a soft, deformable material. And so in the context of ice, again, it starts with those spherical grains of firn, F-I-R-N, but as you have the frictional sliding, as the ice is trying to move, it kind of stretches and bends and pulls the grains in there until they become more elliptical, both because they're getting squished under pressure, which is going to elongate them, but also it's going to elongate them by them being dragged. So these arrows say, yeah, this is getting squished, but you could also very easily put in another arrow pointing this way that says it's getting dragged. And so in this case, the temperature and pressure conditions are such that you don't get melting or you don't get breaking. You get this squishing and dragging within the intense pressure of ice upon ice upon ice on the glacier and the pull of frictional sliding down the hill. So does that make sense? Like if you compare it to deep inside the earth, you got enough heat that it could melt, but there's enough pressure to keep it from melting. And so it flows, just kind of like this. There's enough pressure to keep it solid, but also to allow it to flow. But it's also worth noting that that only happens really deep down, like it's 60 meters or more down. So like a little over, like maybe 3/4 of a football field down is where this starts to happen. Above that, it's still, the pressure isn't high enough and that the ice will break rather than flow. So that's also analogous to like the crust of the earth or the lithosphere of the earth it's high enough up, it's under low enough pressure that it can't have this happen. If you apply too much force to it, it just breaks rather than flowing. So the top of a glacier is kind of like the top of a tectonic plate, and the inside of a glacier is kind of like the mantle underneath it, flowing to transport it. And there even are some places where there actually are ice tectonics, where chunks of ice within glaciers can bump into each other and interact in ways that are very similar to the way tectonic plates do over the mantle. And there's even inferences that like in other parts of our solar system, like for example, Jupiter's moon Europa, looks like it has tectonics, but with sheets of ice behaving like this rather than with rock. So does this make sense? Any questions about just this idea that frozen stuff can still flow? If you're, don't worry again too much about the mechanism of plastic or ductile deformation just yet. We'll talk about that a whole lot more in the metamorphic rocks unit. But I guess I will go on if there are not questions about that. So far we've talked about glaciers as a thing that is on the landscape. They exist either on the tops of mountains or covering continents or even reaching out over the ocean in some cases. They're very much a part of the landscape, but also they can leave distinctive landforms and rock types behind as they move. So even long after a glacier is gone, you can definitely tell that it was there just by what it did to the rock that's left behind. And so for the last part of class, we're just going to talk about some stuff that glaciers can do and some types of rocks, especially sedimentary rocks that it leaves behind, because this is very much part of the sedimentary process now. So glaciers do all this stuff. They weather, erode, transport, and deposit. And so some specific things is like when we were talking about weathering and erosion before. So you can have, glaciers can do that by just surrounding loose rock and moving it with the glacier. Like once that's surrounded by ice, it might as well be part of the ice, right? It's gonna move with the ice. You can also have things where even if the glacier doesn't like literally surround the rock entirely, it can just pull off loose pieces of rock that are sticking out and just drag them along sort of in the interface between the glacier and the rock, just kind of pulling things, kind of like if you remember how we talked about with streams, kind of the bed load, the larger rocks kind of moving, being dragged along the bottom of the stream that the water didn't necessarily pick up, but is still moving. Glaciers can very much do that as well, where they'll pluck rock away from its source and just drag it along on the sides or the bottom of the glacier as it moves, even if it's not within the ice. And then you can also have glacial abrasion, where the ice is just, it's heavy, it's moving and it's heavy, and it can just turn rock into powder. It can just totally pulverize solid rock over time. So do these ideas make sense of how ice can be such an important mechanism for weathering and transportation? And deposit, I mean, the depositing is the glacier melts and moves away and the rocks fall in the place where they were. But any questions about any of those? Cool. So let's talk about some of the features that are left behind. So flowing water can polish rock, it can gouge rock, it can drag things along and leaves marks on them. But ice does so even more, just because it's so much more powerful, and also because it is inherently more abrasive than water. Like water can sandblast, basically. Water can blast things out of the way. But because glaciers themselves are solid ice, they can kind of behave like sandpaper against the rock. And so depending on how rough or smooth they are, depending on how much other stuff is caught up in the glacier, you can get one of two things. So glacial striation on the left here is what happens when the glacier is behaving like really rough sandpaper. And it might either just be because the ice itself is chunky, or it might actually have a bunch of smaller rocks caught up in it. And so what happens is, as the glacier moves and drags itself past another rock, it just scrapes marks into it. Just like if you think about, using rough sandpaper against, like, say, paint or dirt that you're trying to remove, it's going to leave these streaks and rough marks in whatever you're scraping it against. And so in this case, it's happening against a rock. And so you had, if you see the directions of these lines on this rock, that means that the glacier was moving in this back and forth direction across this rock and scraping either ice or small rocks against it to make these deep grooves in the rock. Does that make sense? And then on the other hand, on the right, glacial polish, also kind of what it sounds like. So this is super shiny, but this is not ice. This is granite. Actually, this is in Yosemite. And this rock is so shiny because the glacier polished it down. This is just from the scraping of very fine-grained ice against the rock below. It's like, in this case, if you're using a rough sandpaper to get stuff off of something, you're going to use a very fine grit sandpaper to make it really shiny. And so in that case, the glacier is just behaving like a fine grit sandpaper and wearing down the surface of the rock that it's traveling over until it has a very reflective shine. So this is just a case of, is it coarser or is it smoother? And what is it going to do to the rock underneath it? And actually, if you look at some glacially polished things, like here, you can sort of see some lines indicating the direction of movement. Maybe there were some rocks caught in there, even though most of what was moving was enough to polish it. But it's just that movement back and forth, wearing away either the sides or the base, that leads to these features. So does that make sense? Any questions about either of these? And so it's not just the surface of individual rocks that this process can do, that this removal of material and gouging things out can do. It can actually fundamentally change the shape of entire mountainsides and tops. So like if you remember, the glacier tends to hang out kind of in the top of the mountain. Well, eventually all of that movement and all of that ice is going to just scoop out the rock from the top of the mountain. This ice is powerful, and as it moves, it's going to transport material away from the mountain that is the top of where the top of the glacier hangs out. And so if you have a glacier that was there for a while and then eventually melts, you're going to get left with a scoop. And so this thing on the left it's called a cirque, where a glacier scooped out a circular valley on the top of the mountain. So it's French because there's a lot of these in France in the Alps. they decided to name them. And so you can see it's circular, it's pretty round, because this scoop used to have a glacier in it that then sort of went down the mountain, but now it doesn't anymore. Actually, I guess maybe this stuff might still be glacier and not snow. But can you see how something kind of, as it melted away, would kind of leave behind the bowl that used to contain it? Because that's basically what's going on here. And so sometimes, though, if you have two different glaciers on two immediately adjacent mountaintops, you're going to get what's called an arête, which is another French word that I'm probably pronouncing badly. But in that case, there would have been one glacier here and another glacier over here. And this was just the very narrow boundary between them. It's kind of equivalent to like the drainage divides that we talked about in last class, where all the water on this side is going to go this way and all the water on that side is going to go that way. And in that case, that's what happened with the snow, and kind of formed two different glaciers on either side. And then when those glaciers melted and were gone, it left behind this really pointy boundary between them. And so a lot of these, like cirques are really popular for skiing, arêtes are really popular for rock climbing. A lot of these features are left behind from glacial movement. So yeah, a cirque is a round scoop, circular. An arête is a narrow ridge between glaciers. Any questions about those? So both of these features are technically erosional glacial features, and they mark where the glacier used to be. But there are some other features that exist that actually show more of the movement in addition to the striation and polishing. So basically the shape of a valley can tell you about whether a glacier was there and how far it went. So if a valley is formed only by a river, like in this case on the left, it's going to form a shape like the letter V. Because in this case, the river that's carving out this valley is just at the bottom of it. And even though it's liquid water and it can be quite powerful, it can't carve things out in the same way that ice can. But because that river of ice that is a glacier is a solid mass, it's going to be able to carve out a whole lot more. And so the valleys that are formed by glaciers are a lot more like the letter U. Because here, while you just have liquid water concentrated at the lowest downhill, this you have a giant sheet of ice just blasting everything out of its way. And so you can tell that a glacier at one point moved through a valley if it's shaped like a letter V, or I mean a letter U. But if it's only shaped like a letter V, it was probably only liquid water. So does that make sense? Can you see how ice would scoop out a lot more than water would? I forget where this picture on the left is, but this picture on the right is in Eastern California, kind of near 395 freeway. I actually took this picture on the right, but I don't remember where the one on the left is. It was just a nice example of a V-shaped valley. But another thing that you can tell from glaciers is the stuff they leave behind. So they leave behind a whole lot of rocks. Because ice wins. Ice is going to carry whatever ice wants to carry. It's going to pull rocks from the sides and move them. It's going to drag rocks below them. Basically, if it's in contact with the rock, it's going to move that rock. And so the piles of sediment that's left behind by glaciers is called glacial till. I don't know why it's called that, but it is called that. And it's just sediments of all kinds of stuff, all sizes, ranging from silt to large boulders the size of large boulders. It's just everything. And so when till then consolidates into its own sedimentary rock, it's going to be a very poorly sorted rock. And it's probably going to have a mixture of rounding too. You might have some clasts that are very rounded and some that are very angular, depending on how far the glacier moved them and where it got them. But it's just very poorly sorted, messy stuff that's going to either turn into conglomerate or breccia, just depending on how rounded it is. But in some cases, though, you can get even bigger stuff. Like till is still going to have more small stuff than big stuff. But in some cases, you can get what's called a glacial erratic. And that's a case where you just have a particularly large rock that has been moved very, very far from its source. So usually what happens in that case is like a rock will fall, like you'll have a mass movement and a boulder will fall onto the ice and just move as the glacier moves it. And then as the glacier retreats or melts, that boulder is just going to drop in place. And so depending on how far the glacier went, you might end up having rocks that are dozens or even in some cases hundreds of miles from their source outcrop, from the original rock that they weathered off of. So like this example here, these are the buttermilk boulders, also in Eastern California. And here is a dude for scale. A lot of people go rock climbing on these. These are really, really large, and they're I think they're over 10 miles away from their source outcrop. They're quite far from the top of the Sierra Nevadas, even though if you look at the rock itself, it's exactly the same stuff that's up at the top of the Sierras. It's just not at the top, it's at the bottom because glaciers moved it there. Some of these boulders are the size of houses. People rock climb on them, they're huge. And they're all there due to the power of ice. So does that make sense? By the way, the reason these are called erratics is it comes from error. It comes from erratum. It's from like, this shouldn't be here. That seems wrong. The rocks like this, or this is not near the rocks that it should be near. It doesn't make sense. The only thing that could have put it there is a glacier. Any questions about those? So then the last glacial feature I want to talk about is called a moraine. And so these are super important because they mark where things were, where things went, how far out they got. They are kind of the boundaries between glaciers. So like if an arête is just the boundary between glaciers at the very, very top of the mountain, moraines mark the track of a glacier and its movement. They might separate two glaciers coming down from different things. They might mark the end of a glacier where it stopped. But basically, they're just the signs of movement. They're a lot like the riverbanks, showing this is where the river went, this is where the river of ice was contained. And so, but in the case of ice, it's kind of if you imagine like pushing dirt with a trowel, like, or just shoving sand even with your fist. And if you notice, like when you do that, it forms these long piles showing the track of movement. That's basically what's happening here. It's kind of the ice is pushing things out of the way, and it's piling up in these piles of glacial till on either side. And so these things will be made of till, but the shape that they form is called a moraine. So if they're at the edges of a glacier, they're called a lateral moraine. If they're in the middle of a glacier, it's called a medial moraine. And if at the end of a glacier, it's called an end moraine. I'm not going to necessarily ask you the distinction between these different types so much as what a moraine tells you about a glacier. So this diagram is in your book, but here's an example of some real ones. I think these are also from Eastern California. So in this point, there's no glacier here anymore, but you can very clearly say this is a moraine and this is a moraine, and this U-shaped scoop where the glacier used to be, even though it's retreated, not retweeted, wow, retreated all the way to up here. So does this make sense? So for our last slide, if you remember way back when we were talking about plate tectonics and how people put together the evidence for it, a lot of that came from glaciers. So a lot of it was matching up broken up moraines and U-shaped valleys and striations and polishing. It was just looking for these features that indicated the very specific movement and direction of that movement from glaciers and kind of piecing it back together to understand what has to have happened in Pangaea. So all of these features can tell us about how climate is affecting glaciers now, but they also are really important, not just for shaping the modern landscape of Earth, but also telling us about the history of Earth. So there's a lot of different aspects of geology and different things in this class that tie back into glaciers. And with that, it is 3:15. So that's it for today. If you have any more questions, I'm going to hang out and take them. But if you don't have questions, just keep an eye out for the quick quiz will be up soon. The video will be up soon. The slides will be up soon. And the poll for what you want me to go back over on Monday will also be up soon. So have a good one.
Thank you, Professor. Have a good one.
Thank you, Professor. Have a nice day.
Thanks. Have a good one. So, Israel and Vanessa, are you still taking notes, or are you just kind of zoned out? Okay. So, if you are just kind of zoned out, I mean, I guess if you do have a question, I have another meeting right after this. So if you have a question, just don't hesitate to email me at any time. I will get to it as soon as I can. So talk to you later.